In July 2023, deep in the North Atlantic, something started happening to the water. And I'm not talking about, a little warm patch or a freak wave. I'm talking about the Atlantic Meridional Overturning Circulation, the AMOC.
The Great Conveyor Belt.
Right, exactly.
Huh.
This is the massive system of currents that pulls warm water up from the tropics and essentially keeps northern Europe from turning into a popsicle. It's the radiator of the planet.
Yeah.
And in July 2023, it started to, twitch.
Which is a very good word for it.
Scientists were looking at the sea surface temperature data, and it wasn't just that the baseline was rising, it was the way the temperature was moving. Day to day, it was swinging wilder and wilder. The variance was just spiking.
It's the wobble.
That's exactly the feeling I get when I look at the charts. It looks like a spinning top right before it falls over.
Yeah.
It starts to wobble.
And if you are a physicist, that wobble has a very specific and, frankly, a very scary name. It's called critical slowing down. It implies that the system, this massive ocean current, is losing its ability to recover from a punch. It gets hit by a storm or a heat wave, and instead of bouncing back instantly, it drags, it lingers.
And that sluggishness is the harbinger of doom, is the mathematical signature that just screams, I'm about to break.
Correct. It is the last thing you see before a collapse, a catastrophic shift.
But here's the thing that really, really rattled me when I started digging into this research. That exact same mathematical signature, that distinct, terrifying wobble, didn't just happen in the ocean in 2023. It appeared in the S&P 500 stock index in the months leading up to the 2008 financial crash.
It was there. The data is unambiguous.
And it appeared in the vegetation index data from the Sahel region in Africa right before thousands of years of grassland just collapsed into the Sahara Desert.
Same signature.
And, just to make it completely bizarre, it appears in a simple bar of iron sitting on a lab bench as you heat it up towards 770 degrees Celsius.
Which is the Curie point, the point where it stops being a magnet.
Exactly. So, okay, let me get this straight. We have an ocean current, a stock market, a desert, and a magnet. They're made of completely different things. They operate on completely different scales of time and space. And yet, right before they fail, they all speak the exact same mathematical language. Why?
That is the question, isn't it?
Why do ice sheets and hedge funds break in the exact same way?
It's a question that leads us to one of the deepest, most beautiful, and frankly most surprising results in 20th century physics. It suggests that tipping points aren't just metaphors we use on the news. They are a fundamental property of the universe's geometry.
Welcome to Relatively Human. I'm your host.
And I'm your co-host.
Today we are doing a deep dive into the physics of failure. We're looking at tipping points and honestly looking at the stack of research we have on the table today, from Nobel Prize-winning condensed matter physics to ecology to high-frequency trading. This feels less like a science lesson and more like we're trying to decode the source code of reality.
That's because in a way we are. I really want to set the stakes very clearly here at the top. Usually when you hear tipping point in the media, it's a buzzword. It's kind of vague. It just means something bad is about to happen.
Right. The tipping point of the election, or, the tipping point of my patience with my kids.
Exactly. But in physics, a tipping point is not a metaphor. It is a precise mathematical object. And the fact that this same mathematics shows up in economics and biology is not a coincidence. It is not an analogy. It is a structural identity.
Okay, that is a massive claim. You're saying the stock market crash in 2008 and a piece of iron losing its magnetism aren't just like each other. You're saying they are mathematically the same event.
Structurally, yes.
Yeah.
At a deep fundamental level, the dynamics are identical. And today we're going to unpack exactly why. We're going to do this in 3 parts because we need to build this really carefully. First, we have to understand the hard physics, the Tier 1, established, Nobel Prize-winning science of how things break. That's our Act 1.
Okay. And then in Act 2, we'll look at the crossover, how this physics jumped the fence into ecology, into climate science, into finance, and the evidence that supports it. We'll look at the wins, and we'll also look at the critiques, because there are some very valid ones.
Absolutely. And finally, in Act 3, we're going to step off the map. We're going to the edge of what is known. We're going to look at a new framework that suggests the hidden variable controlling all of this might be, of all things, dimensions. Not parallel dimensions, but the geometry of the space the system lives in.
And just a heads up for you listening, we are going to be really rigorous about confidence levels today. When we are talking about established physics, we will tell you. When we are entering the realm of conjecture and new theories, we will flag that very, very clearly.
Absolutely. Precision matters here more than almost anywhere else.
Okay, let's unpack this. Act 1, the physics of breaking. You mentioned that tipping point is the colloquial term. What did the pros call it?
The technical term is a phase transition.
Okay, phase transition. That sounds like high school chemistry, like water freezing into ice.
Exactly. That is the textbook definition. It's the perfect place to start. You have a system, say, a bucket of water, and you change one external parameter, which is temperature. As you lower the temperature, say from 20 degrees Celsius down to 10 degrees, nothing dramatic happens. The water just gets colder. It's still a liquid. The molecules are still sliding past each other chaotically.
It's a linear change, a smooth change. Lower temp, colder water. Simple.
Until you hit 0 degrees Celsius. This is the critical point. And suddenly, discontinuously, the behavior of the entire system changes. Liquid becomes solid. Order emerges from disorder. The H2O molecules lock into a crystal lattice.
Okay, I get freezing, but that feels, I don't know, kind of simple. It gets cold, it turns to ice. Where's the universal law in that? It feels very specific to water.
You're absolutely right. Water is actually a bit messy for this because it expands when it freezes and does all sorts of weird chemical things. To see the universal law, we need to strip it down. We need a cleaner system. So let's swap the water for a magnet. Specifically, a ferromagnet, like a simple bar of iron.
Okay, I'm picturing a gray bar of iron sitting on a table.
At room temperature, that iron is magnetic. Why? Because inside the iron, the individual atoms act like tiny little compass needles. We call them spins. And at room temperature, all those spins are aligned. They're all pointing north, let's say. Because they are aligned, their tiny magnetic fields add up and create one big macroscopic magnetic field.
Got it. Aligned spins equal magnetism. Order equals magnetic field.
Now let's start heating that iron up. Heat is essentially thermal noise. It's kinetic energy that wants to jiggle those atoms around to introduce chaos. So as you raise the temperature, you are introducing this random energy that's trying to flip those little compass needles.
So it's a battle. The atoms want to align because the fundamental magnetic force is between them, but the heat wants to scramble them.
Precisely. It is a tug of war between order and entropy. And for a long time, as you heat it, 100 degrees, 200, 500 degrees, the alignment wins. The magnet stays magnetic. It gets a little weaker, sure, but the overall structure holds.
It's resilient. It could take the heat.
But as you get closer and closer to a specific temperature, the Curie point, which for iron is roughly 770 degrees Celsius, something very strange starts to happen. The system gets indecisive.
Indecisive. It's a rock. How can a piece of metal be indecisive?
It gets correlated. This is the key concept. Far away from the tipping point, at room temperature, the system is stiff, rigid. If one atom tries to flip, its neighbors immediately force it back into line. The correlation length, which is the distance over which fluctuation travels, is very short, maybe a few atomic spacings.
Okay, so the gossip doesn't travel far. A little rebellion in one corner is squashed instantly.
Exactly. But as you approach 770 degrees, the heat is loosening those bonds. The system is on the very edge of losing its order. Now, if a group of atoms flips, they don't get squashed immediately. They might actually persuade their neighbors to flip too. And those neighbors persuade their neighbors.
The rebellion spreads, the gossip goes viral.
Rapidly. And right before the magnetism vanishes completely, that correlation length starts to diverge. In the mathematical limit, it goes to infinity.
Wait, infinity?
Yeah?
In a physical object? That sounds impossible. How can a signal travel infinitely far in a finite bar of iron?
It's a mathematical limit, but what it means physically is that the correlation length becomes as large as the system itself. Suddenly, every part of the system is talking to every other part. You start getting these patches of aligned spins, but not just small patches. You get small patches inside medium patches, inside massive patches. The system becomes scale-free.
Scale-free. That implies that if I zoomed in with a powerful microscope or I zoomed out with a telescope, the pattern of these magnetic islands would look statistically identical.
Exactly. There is no characteristic size anymore. The fluctuations, the wobbles, happen at every single magnitude. And because that correlation length is diverging, the system becomes incredibly sensitive. A tiny flick of a single spin in one corner can trigger a cascade that ripples through the entire system. This is why we see that dramatic increase in variance we talked about in the intro. The system is flickering between states. It's wobbling because it literally doesn't know which way to point anymore.
So the wobble is the physical manifestation of the system acting like a single, giant, interconnected entity rather than billions of separate independent atoms.
You nailed it. And this specific behavior, how all these quantities change near the critical point, is described by a specific set of numbers called critical exponents. These are the numbers that describe the power laws governing the system. How fast does the magnetism vanish as you approach the temperature? How fast does the correlation length grow? These are precise numbers, specific values like 0.326 or 1.24.
Okay, so we have these specific, almost magical numbers that describe how iron loses magnetism. I have to assume we have different numbers for how water boils or how liquid helium becomes a superfluid. I mean, helium's a light gas, iron is a heavy metal. They're totally different beasts. The forces are different, the particles are different.
Logic would absolutely dictate that, right? The details have to matter. Iron atoms are heavy and stuck in a grid. Helium atoms are light and sloshing around. The forces are different. The chemistry is different. They should break differently.
Right, they have to.
But this is where the universe throws one of its biggest curveballs. In the 1960s and 70s, physicists discovered something called universality.
I love that word. It sounds religious, almost philosophical.
It's almost spiritual for physicists, I think. It started with a physicist named Leo Kadanoff, that's K-A-D, on a true giant in the field. In 1966, he had this incredible insight. He looked at this scale-free behavior in the magnet and said, if the system looks the same at any zoom level, then I should be able to blur my eyes.
Blur his eyes. What does that mean mathematically?
He called it coarse graining. Think of it like a digital photo. A high-res photo is made of millions of tiny pixels. If you zoom all the way in, you just see a red dot next to a blue dot. You see the microscopic detail.
Right, the individual components.
But if you shrink that photo by 50%, you lose the individual pixels. You average them out. A block of 4 pixels becomes 1 superpixel. But the image, the face, the landscape, it's still there. The microscopic structure is preserved. Kadanoff realized you could do this with the magnet. Take a block of spins, say, a 2x2 grid, and average them into one single superspin. Then take a block of those superspins and average them again.
So he's zooming out. He's actively, deliberately ignoring the individual atoms to see if the larger pattern survives the process.
Yes. And then Kenneth Wilson took this idea and formalized it into a mathematical machine called the renormalization group, which won him the Nobel Prize in 1982. Wilson proved something so profound it changed physics. He proved that when you do this coarse graining, when you keep zooming out, washing away the microscopic details, the specific personality of the atoms just disappears. The atomic weight of iron washes away. The strength of the chemical bonds washes away. The viscosity of the fluid, gone.
Wait, hold on. If you wash away all the details, what is left? There's nothing left to describe.
That's what you'd think. But 2 things survive the process. Just 2. First, the spatial dimension the system lives in. Is it 2D, like a flat sheet, or 3D, like a solid block? And second, the symmetry of the order parameter. Essentially, can the spins point only up and down, or can they rotate freely in a circle or a sphere?
Hold on. You're telling me that if I have a magnet in 3D space and say a mixture of oil and water in a beaker, also in 3D space, and they both happen to have the same symmetry,
Yeah.
they will break in the exact same way.
Identically, to
Yeah.
6 decimal places.
That is just wild. You're telling me a fluid made of complex organic molecules and a solid metal crystal follow the same math.
It's the concept of universality classes. The 3D Ising model, which is the math for the magnet with up-down spins, that's pronounced EE-zing, and the 3D binary fluid mixture belong to the exact same universality class. They're made of different stuff with different forces at different temperatures, yet they share identical critical exponents.
Okay, but can we verify this? Or is this just beautiful math on a chalkboard that we have to take on faith?
Oh, it is verified beyond any reasonable doubt. We have a powerful theoretical technique called the conformal bootstrap, Elshouk, and collaborators did incredible work on this in 2014, which calculated these exponents theoretically to extreme precision. And when you go into a lab and you measure them, heating up iron or pressurizing fluids near their critical point, the numbers match perfectly. We're talking about knowing how the universe breaks to the 6th decimal place. It is one of the most precise and stunning agreements between pure theory and messy experiment in all of science.
So the Act 1 punchline is, how a system breaks is determined not by what it's made of, but by the geometry of the space it lives in.
Correct. Dimension and symmetry are the master variables. Everything else is just details that get washed out at the critical point.
Okay. I need to take a breath here because
Right.
it's a lot. It's a huge idea. We've established that in the world of physics, atoms, fluids, magnets, the nitty-gritty details don't matter near a tipping point. Only the connections and the dimensions matter.
Right. That's the core takeaway.
But I'm not made of iron. The stock market isn't made of liquid helium. The Amazon rainforest isn't a binary fluid. We are complex, messy, adaptive systems. Does the universe really treat a Wall Street trader panicking and selling his stocks the same way it treats an iron atom in a crystal lattice?
That is the ultimate question. If universality is truly universal, it shouldn't stop at the edge of the physics lab. It should bleed out into the rest of the world.
Which brings us to Act 2, the crossover. This is where we move from pure hard physics into the messy real world. We are entering Tier 1-2 territory here. We have strong evidence, but also real debate and real complexity.
And let's start with ecology. Because an ecosystem is arguably the most complex system we know. So much feedback, so many interacting parts.
There's a landmark paper, I think it was 2009, by Martin Scheffer.
Yes, Scheffer, that's pronounced Scheffer. And his team published this incredible paper in Nature. They were looking at shallow lakes. Now, picture a beautiful, clear, shallow lake. The sunlight can penetrate all the way to the bottom, so healthy vegetation grows there, which in turn keeps the sediment trapped. It's a clear water, stable state.
Okay, a healthy lake.
But now, imagine a farm nearby starts having fertilizer runoff, nitrogen, phosphorus. The lake can handle it for a while. It absorbs the nutrients. It stays clear. It's resilient. But eventually, the nutrient load gets too high. It crosses a threshold. It hits a tipping point.
The phase transition.
Exactly. And suddenly, the system flips. The bottom-dwelling vegetation dies off, the sediment gets stirred up by wind and fish, and algae, which loves those nutrients, blooms everywhere. The water turns into a turbid green soup. And here's the kicker. Once it flips to the green soup state, it is incredibly hard to flip it back. Even if you completely stop the pollution, the algae has taken over and it stays. This is a phenomenon called hysteresis.
You get stuck in the new bad state.
Scheffer's big question was, can we see the green soup coming? Before the vegetation dies, before the whole system crashes, does the lake warn us?
And did it? Please tell me it did.
It did. They analyzed the data, the fluctuations in chlorophyll levels day to day, the water clarity, and they found the ghost of the magnet.
The ghost of the magnet. I like that.
They found critical slowing down. Just like the iron spins getting more and more correlated as they approached the Curie point, the lake's biological processes started showing increased autocorrelation.
Walk me through autocorrelation in a lake. That sounds a bit abstract.
Sure, it's a measure of memory. Think of it this way. If a system is healthy and resilient, and you poke it, say, a big storm churns up the water for a day. It bounces back very quickly. So today's state doesn't depend much on yesterday's perturbation because the system erased it. It forgot the punch.
It's elastic. It snaps back.
Precisely. But as a system loses resilience and approaches a tipping point, it gets slow, sluggish. It can't recover as fast. So the state of the lake today becomes very, very similar to the state of the lake yesterday, which was similar to the day before. It drags its past along with it like a heavy chain.
That's the sluggishness, the wobble.
Yes. And that shows up mathematically as rising autocorrelation and, just like the magnet, rising variance. The system flickers more wildly. Scheffer and his colleagues showed this happens in lakes, in coral reefs as they bleach, and seemingly in the global climate system itself.
Which brings us right back to the AMOC, the current we started this whole deep dive with.
Right. This is the work of Tim Lenton and his colleagues. This was a huge 2008 paper in PNAS, where they cataloged the tipping elements of the Earth system. They identified 9 massive components that could have these critical thresholds: the Amazon rainforest, the Indian monsoon, the Greenland ice sheet, and of course, the AMOC. Lenton's argument is that these are all systems approaching a bifurcation point.
Bifurcation. That's another math term, right?
It is. The analogy everyone uses is a ball in a valley. Picture a ball sitting at the bottom of a nice, deep valley. That's a stable state. The ball is the climate. The valley is the current temperature range we live in. Gravity keeps the ball at the bottom.
Simple enough. Poke it, and it rolls back down.
Exactly. But now imagine the landscape itself is changing because of rising CO2 levels. The floor of the valley is slowly rising. The walls of the valley are getting shallower and shallower. Eventually, the valley bottom becomes flat. And then it becomes a hill.
And the ball can't sit on top of a hill. It's unstable.
Right. It has to roll off. It will inevitably roll into a new valley, maybe a much deeper, hotter, hothouse Earth valley. That moment when the valley becomes a ridge is the bifurcation.
And I'm guessing that before the valley completely disappears, as the walls get shallower, the ball starts to wobble more.
Exactly. The restoring force, the steepness of the valley walls that pulls it back to the center, gets weaker and weaker. So the ball wanders more, it flickers, it has higher variance. That's the signal we saw in the Atlantic in July 2023. It's the ball rattling around because the valley it lives in is disappearing.
It is genuinely incredible that a lake and a magnet and an ocean current share this exact behavior.
Yeah.
But let's talk about the one that hits everyone's wallet, the financial markets. This is where Didier Sornet comes in.
Sornet, that's pronounced Sornet, is a physicist at ETH Zurich. He's a fascinating character, a true polymath. He looked at Wall Street and said, this isn't economics. This is a system of interacting agents. He wrote a seminal book back in 2003 called Why Stock Markets Crash.
So in his view, the traders are the atoms, the individual spins.
Basically, yes. In a magnet, the spins align because of quantum mechanical exchange interactions. In a market, traders align because of, well, psychology. Fear and greed. Herding behavior. FOMO.
Oh, I felt that. I see you buying that stock, so I'm going to buy it. I don't want to be the idiot holding cash while everyone else gets rich.
Exactly. Imitation. It's a coupling force. Sornet argues that financial crashes are critical transitions. They are not random black swan events caused by some bad news report from the outside. They are endogenous. The system builds up instability from the inside through its own feedback loops.
And does it show the wobble, the critical slowing down?
Sornet identified a different but related signature, a very specific one called log periodic oscillations.
Okay, that's a mouthful. Let's unpack it. Log periodic oscillations.
So imagine the price of a stock going up during a bubble, a speculative mania. It doesn't just go up in a smooth, straight line. It has waves. It oscillates up and down, even as the overall trend is upward. Sornet noticed that before a massive crash like 1929, 1987, the dot-com bubble, the frequency of those waves speeds up.
Speeds up how? Like they get more frequent.
The time between the peaks of the waves gets shorter and shorter. So at first it's peak, long pause, peak, shorter pause, peak, little pause, peak, 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 peak. It accelerates into the crash.
Like a fighter jet engine winding up to a higher and higher pitch right before it explodes.
This is a great analogy. Or like a bouncing ball coming to rest. Bounce, bounce, stop, beep, 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 stop. The spacing between the peaks shrinks by a constant ratio. It's a very specific geometric pattern. And mathematically, it looks suspiciously like the famous Feigenbaum constants that you see in the route to chaos.
So the market starts vibrating faster and faster until it just shatters.
That's the theory. The herding behavior creates these positive feedback loops, super exponential growth that simply cannot be sustained. The crash is the phase transition. It's the collective order breaking down to restore some kind of balance.
Now, I have to play the skeptic here, as promised. If this is true, why aren't we all rich? Why can't we just run a Sornet algorithm on our laptops and know to sell everything next Tuesday?
That is the billion-dollar question. And this is exactly why we are in Tier 1-2 territory, not solid Tier 1. Sornet and his group have made some genuinely successful predictions. He famously called the Shanghai crash in 2009, but they're also false positives. Times the signal appears and nothing happens.
The crystal ball is cloudy.
Markets are incredibly messy. They have so much noise. Unlike a pristine crystal of iron in a vacuum lab, the market is getting hit with external shocks constantly. Wars, elections, pandemics, a tweet from a CEO. So while the internal structure of the crash looks like a critical point, using it as a precision timing tool is exceptionally difficult. It's more of a diagnostic, not a prophecy.
Fair enough. It tells you the ice is getting dangerously thin, not the exact millisecond you'll fall through.
Exactly.
I want to touch on one more big concept in this act.
Yeah.
Two before we move on. Self-organized criticality. This is the famous sandpile model, right?
Yes. Per Bach, Chow Tang, and Kurt Wiesenfeld. A huge paper from 1987. This is a really profound idea. In the magnet example, remember, we had to carefully tune the temperature to exactly 770 degrees to see the critical behavior. We had to turn the dial.
Right. But nature doesn't have a giant hand in the sky tuning a dial for earthquakes or forest fires or stock markets.
Exactly. Bach asked, why do we see power laws everywhere in nature? The size of earthquakes follows the Gutenberg-Richter law, the size of solar flares, the size of neuronal avalanches in the brain. Who is tuning them to the critical point?
And the answer was the sandpile.
Imagine dropping grains of sand one by one onto a flat table. At first, nothing much happens, but eventually a pile forms. The pile gets steeper and steeper. Eventually, it reaches a critical state, a critical angle of repose. If you drop one more grain of sand, it might just stick, or it might trigger a tiny slide of a few grains. Or it might trigger a massive avalanche that collapses the entire side of the pile.
And you have absolutely no way of telling which one it will be.
No. But if you sit there for hours and measure the size of all the avalanches, big and small, their sizes follow a perfect power law. Small ones are common, huge ones are rare, but they follow a strict mathematical ratio. The key insight was that the system tuned itself to the critical point. If the pile gets too steep, a big avalanche flattens it back to the critical angle. If it's too shallow, the sand just builds up until it reaches the critical angle.
So the system naturally wants to live on the edge of instability. That's its most stable state, paradoxically.
Yes.
Yeah.
Back argued that many complex systems in nature are self-organized critical. They naturally evolve to the tipping point and hover there, because that is the most efficient state for them to be in to transport energy or information.
Now, to keep us honest, I know there was a really important paper in 2009 by Closet, Shalizzi, and Newman that threw some cold water on this whole power law party.
It was a necessary and brilliant splash of cold water. For a while, in the 90s and early 2000s, scientists were finding power laws in everything. The pattern of cities, the frequency of words in a book, the number of casualties in wars.
It became a trend. If you had data, you looked for a power law.
Closet and his team developed much more rigorous statistical methods and went back and looked at a lot of these famous empirical data sets. They said, hey, wait a minute. If you just squint at the graph, it looks like a power law, a nice straight line on a log-log plot. But if you do the proper rigorous statistics, a lot of them are actually better fit by other distributions, like a log normal or a stretched exponential.
So they aren't true critical points. The math is different.
In many cases, no, they are not. And that intellectual honesty is absolutely vital. We shouldn't force the data to fit our beautiful theory just because the theory is beautiful. But, and this is the really important part, the critique didn't kill the field. It strengthened it. It forced everyone to be more rigorous. The cases that survived the closet critique, like the Gutenberg-Richter law for earthquakes, for instance, are now on much, much firmer ground.
Okay, so where does that leave us at the end of Act 2? We know for a fact that physics has this precise concept of universality based on dimension. We know that ecology and finance show these eerie, compelling echoes of the same mathematics, even if the real-world data is messier. But the big question remains, why is it the same? Why does the ghost of the magnet haunt the stock market?
That brings us to Act 3, the dimensional key. And here, I need to pause and put up a big flashing neon sign for everyone.
Warning. Entering conjecture territory.
Exactly. We are leaving the safe harbor of Tier 1 and Tier 2 science. We are now moving firmly into Tier 3. This is the dimensional scaling framework. It's a set of hypotheses that tries to unify all of this. It's speculative, but it's powerful.
Let's start with the foundation. We talked about how dimension is one of the two master variables. 2D magnets behave differently than 3D magnets.
Right. The critical exponents depend on D. We know the values for D1, D2, D3, and so on.
But the real world isn't always perfectly 1D, 2D, or 3D, is it? It's much weirder than that.
No. And this is where Benoit Mandelbrot enters the chat. In the 60s and 70s, he popularized the concept of fractals. Think about a simple piece of paper. That's a 2D object. Now crumple it into a tight ball.
Okay, got it.
Is it still 2D? Well, the paper itself is, but the ball now takes up space like a 3D object. But it's not a solid sphere. It's full of gaps and voids. It's somewhere in between 2D and 3D.
It's a fractional dimension.
Exactly. Or his classic example, the coastline of Britain. If you measure it with a mile-long ruler, you get one length. If you use a foot-long ruler, you can measure all the ins and outs of the bays, and the total length gets much longer. If you use an inch-long ruler, you measure the pebbles on the beach, and it gets huge. Mandelbrot showed that coastlines have a fractional dimension. Britain's is roughly 1.25 dimensional.
That is so trippy. My brain hurts a little just thinking about that.
It is. And it's not just a mathematical curiosity. The vascular networks in your body, the way veins and arteries branch to fill tissue, have a fractal dimension between 2 and 3. They are volume-filling networks. The structure of a tree is fractal. So here is the hypothesis. If dimension determines how things break, and real-world systems like stock market networks or neural networks have these weird fractional dimensions, then shouldn't their breaking behavior also be fractional?
That is the core of a specific hypothesis we can call conjecture P8. It proposes that effective dimensionality, we call it dea, is the hidden variable. The claim is that if you simulate a magnet, an Ising model, on a fractal shape like a Sierpinski gasket, which is a triangle full of holes with a dimension of about 1.585, The critical exponents you measure shouldn't be random numbers.
They should fit the pattern. They should land somewhere between the 1D and 2D values.
Not just somewhere. They should fall on a smooth, continuous curve connecting the known 1D values to the known 2D values.
Wait, so instead of these discrete jumps from universality class A to universality class B, you're proposing there is a rainbow, a continuous spectrum of universality.
That is the prediction, a continuous spectrum of universality classes, parameterized by the effective dimension, day-f gap. Has anyone tested this? This seems like something you could test with a big enough computer.
Partially. Way back in 1980, Giffen and others did run some early simulations on fractal lattices, and they did find that the physics was different from the integer dimensions. But we haven't yet done what we can call the gate G5 experiment.
Gate G5. Sounds like a secret clearance level at Area 51.
It just stands for Gateway 5 in the framework. It's the decisive test. We need to run very high-precision simulations using modern techniques like finite-size scaling on these fractal shapes. We need to apply the same conformal bootstrap rigor to the Sierpinski gasket, which is a shape pronounced Sierpinski.
And what are we looking for, specifically? What's the pass-fail?
If the critical exponents we calculate land exactly on the smooth curve predicted by the hypothesis, it's a massive breakthrough. It would mean dimension is continuous in the eyes of physics. It would mean you can have a 1.585 dimensional phase transition.
And if they don't? What if they just snap to the nearest integer?
If they cluster around the integer values, if the universe says, no, sorry, you're either 1D or 2D, pick one, then the conjecture fails. And that is perfectly fine. That's how good science works. It has to be falsifiable.
But if it is true, what does that mean for the stock market or the Amazon?
This is where it gets really practical. If this hypothesis holds, then every complex network, the web of banks in the financial system, the power grid, the internet, the connections between neurons in your brain, has something called a spectral dimension. It's a number you can calculate based on how the nodes are connected to each other.
So we could literally map the stock market and calculate its dimension.
We could calculate the effective dimension of the trader network. And let's say, for argument's sake, the dimension of Wall Street comes out to be 2.4. We would then look at our universal curve, and it would tell us exactly what the critical exponents for a crash should be. It would tell us precisely how the wobble should look before the system breaks.
It turns dimension into a diagnostic tool, a predictive tool.
Precisely. We could look at a coral reef and say, the fractal dimension of this reef's connectivity is X, therefore its resilience to a temperature shock is Y. It gives us a way to predict the tipping point based on the pure geometry of the connections.
We discussed urban scaling briefly in the prep for this, the work by Louis Betancourt on how cities grow.
That fits in here too, right?
It fits perfectly. It's a real-world example of this kind of dimensional scaling. Betancourt showed that cities scale in predictable ways, but different things scale differently. A city that is twice as big in population doesn't just have twice as many gas stations or twice as many miles of road. It has less than twice as much because of efficiencies. It's sublinear. But a city twice as big produces more than twice the GDP, more than twice the patents. That's super linear.
So why the difference? The infrastructure, the pipes, the roads, is constrained by 2D or 3D space. It scales with a low effective dimension. But ideas, wealth creation, that happens in the social network. And social networks are high dimensional. You can talk to 100 people. An idea can spread through the network almost instantly. It's not constrained by physical pipes. It scales with a higher effective dimension.
So the effective dimension of the interaction determines the scaling law. It's the same principle.
Exactly.
Before we wrap up this very speculative Act 3, I want to touch on the point of no return. We mentioned that sometimes when things tip, they don't tip back.
Hysteresis.
This is the Humpty Dumpty problem.
Yeah.
All the king's horses and all the king's men.
It is. In physics, we use something called the Pryzak model. That's P-R-Y-Z-A-K. It's a way of categorizing all the different ways systems can get stuck. The really scary one is called type 5 hysteresis. In math terms, it's a paired saddle node bifurcation.
Okay, translate that for me into English.
Okay. Imagine you push a system over a climber. It falls into a very deep, stable hole. To get it back to where it was, you can't just lift it a little bit. You can't just reverse the push. You have to lift it way higher than the original cliff edge to get it out of that deep new hole.
So if the Amazon rainforest crosses a tipping point and turns into a savanna, simply restoring the historical rainfall levels might not be enough. You might need super rain for 100 years to get the forest back.
Yes. The path forward is not the same as the path back. We call this overshoot. You have to significantly overshoot the original conditions to restore the system to its previous state, if you can restore it at all.
And there's also something you mentioned called rate-induced tipping.
Type 6. This is absolutely critical for climate change. Sometimes it's not about how hot it gets, it's about how fast it gets hot. If you change the parameter like CO2 in the atmosphere very, very slowly, the system can adapt. It stays in its stable valley even as the valley moves. But if you change it too fast, like our current rate of CO2 emissions, the system can't track the moving equilibrium. It essentially falls off the back of a moving train.
It's the speed that kills, not just the destination.
Exactly. Reperfusion injury in biology is a perfect and tragic example. If someone has a heart attack, a loss of oxygen to the heart muscle, and you then flood the tissue with oxygen too quickly, the cells die. The return of oxygen was too fast. The system couldn't adapt to the rate of change, and it led to catastrophic failure.
Wow. Okay, that brings a whole new level of anxiety to the climate conversation. It's not just a temperature target we need to worry about, it's the velocity at which we approach it.
Correct. The rate is its own tipping element.
Okay, my brain is officially full. Let's bring this in for a landing. We've covered a lot of ground, from the atomic spins of iron to the trading floors of New York, all the way to the bizarre geometry of fractional dimensions.
We have.
Let's do the confidence score. I want to wrap this up responsibly for everyone listening. What is solid rock and what is interesting speculative vapor?
Okay. Tier 1 established. Universality. The renormalization group. The fact that dimension and symmetry dictate critical exponents. This is confirmed to 6 decimal places. If you bet against this in a physics department, you lose. That is bedrock.
Check, solid ground.
Tier 2, strong evidence debate. The application of these ideas to ecology and finance. We clearly see the signatures, the critical slowing down, the power laws in lakes, climate models and markets. The physics structure is undoubtedly there, but the predictive power, that is still a research program. It's being refined. The data is noisy, and as Claus had taught us, not every curve is a power law.
And Tier 3, the really out there stuff.
Tier 3, conjecture, the dimensional scaling framework. The idea that effective dimension is a continuous variable that governs a continuous spectrum of universality. It is a beautiful, elegant, and crucially, a falsifiable hypothesis. But right now, it is waiting for that gate G5 computation to confirm or deny it.
And what is that one experiment again? The one computation that could decide it?
The Ising model on fractal substrates. We need to run that simulation with modern high-precision methods. If the exponents interpolate smoothly between the integer dimensions, we have found a new, deep key to physics.
I love that. We are literally one big computer simulation away from knowing if this grand unifying connection is real.
It makes you wonder what else is hiding in the simple geometry of the world around us.
So final takeaways for the listener. What are the 3 things they should remember from all this?
3 things. 1, tipping point is not just a buzzword. It is a rigorous mathematical concept that defines how order turns to chaos, and it has specific measurable signatures. 2, the fact that markets and magnets and ecosystems break in similar ways is structural, not coincidental. They are all systems of interacting, coupled agents facing the relentless forces of entropy. The math doesn't care about the details.
And 3.
And 3, we might be on the verge of proving that dimension-pure geometry is the master variable that decides the fate of nearly every complex system, from our brains to our planet.
That is a lot to chew on. Next time you see the stock market wobble on the news or read about the ocean current slowing down, just remember the magnet.
It's all the same math hiding in plain sight.
Thanks for joining us on this deep dive.
Thanks for having me. It was a pleasure.
I'm your host, signing off for Relatively Human. Stay curious.
And stay critical.